Hello students, welcome back. Let's resume our discussion in section 2. Previously, we established the fundamental theorem of finitely generated abelian groups, and then we did some example problems associated to it. Now the final topic that we didn't cover yet is example 2.7, and it looks pretty benign. Let G be a finite abelian group of order M, and let D be a positive integer that divides M. Prove that G has a subgroup of order D. Let's see. Have you seen this before? Or something very, very similar to it? You've seen it, not in a finite abelian group version, but in finite cyclic group version. This one we have. Let G be a finite cyclic group of order M, and let D be a positive integer that divides M. Then G has a subgroup of order D. This one we have. We did it twice actually. Once in lesson 4 when we did cyclic groups, and then once in lesson 6 when we revisited for a review, partly, and also in parts to review Lagrange theorem. Remember Lagrange theorem? The order of subgroup divides the order of the original group. Now this one is partial converse for a special case for cyclic groups. And then of course we have to do that for finite abelian groups. So it goes kind of like this, that G is a cyclic group of order M, and then let's see, D divides M, then there exists a subgroup H such that this one we did. And how did he define this H? Remember that too? Well, we define it like this. A to the M over D power. So D divides M, so M over D is actually an integer. And then, yes, it'll turn out that this is a subgroup of G, of course, and it has order precisely D. Let's see, what if we write everything in terms of addition version? Because we are dealing with abelian groups, so the cyclic group version written in power form and multiplication form may be a little bit misleading. So instead of that, I can write as like this. So we are doing repeated multiplication here. Yeah, this is for repeated multiplication. And this one is written for repeated addition. So this A to the M over D power, or in general, in this case, A to the K power is A times dot dot dot, which is repeated K time. And this one down here, the coefficient expression, is kind of like this. repeated k times. So the expression down below is going to be a little bit more useful for this proof. So let's not worry about this. Let's remove that. And let's keep this here as a reference. We did it already, and if you're unsure, you can always go back to lesson 4 or lesson 6 and restudy that. Now let's come back to the original problem. Let G be a finite abelian group of order m. So if you go back to the fundamental theorem, Betti number is 0. We don't have any of those. If we do, then we no longer have finite group. And m is gonna be the order of the group. So m will be p1 to the r1 power times p2 to the r2 power all the way up to, like this, pn to the rn power. So we have a prime factorization of m, and that's going to be a kind of trick that you can use. Okay, so much for preparation. Now let's begin. We have to do it in multi-step process, and let's begin with the prime factorization. From the fundamental theorem, we can rewrite G like this, because G is isomorphic to this expression, and consequently the order of the group can be rewritten like this, and we're going to have a prime factorization. I'm calling it a prime factorization, not the prime factorization, because there could be some duplicate. You see, here, those pi's are not necessarily all distinct. There could be some duplicates. Keep that in your mind. Now D divides M, so it can be written in similar prime factorization like this, with all those, with S1 to the Sn power, and then Si should be less than or equal to Ri power. If Si is greater, then that factor will not divide this factor. But then again, this follows immediately if you have the prime factorizations from the fundamental theorem of arithmetic or the unique factorization theorem, but it's not coming from there. It's coming from this fundamental theorem of the finitely generated abelian groups. So some of those pi's may be duplicate. Does it matter? Actually, it does not. You can redistribute the power kind of like this, as you can see in this kind of example, so that we can fill up to this, and then as much as you can fit in, go in there. You see, 32 is actually 2 to the 5th power. So if you consider 2 to the 5th power directly dividing this or that, nothing works. But if you redistribute this 5 appropriately, 2 to 1 like this, then it's okay. So put it into first as much as possible, and then to the second as much as possible, and then to the third as much as possible until you run out. If you do not run out, then this is not going to be a factor. Okay? So these may not be the prime factorization, but we still have this property. P1 to the S1 power, P2 to the S2 power, and so on, Pn to the Sn power, where all those powers, Si's are less than or equal to Ri's, so that each power divides corresponding power. We claim there's a subgroup of H of G which is isomorphic to this. Consequently, the order is D. So Z of P1 to the S1 power, which I just highlighted in blue, which corresponds to this factor here, and that divides the first factor here for M, and that's going to be a subgroup of this, blue. And then similar, and then in the end, yes, this one green, which corresponds to Pn to the Sn power, this one here, and then that divides this power factor, and then this part is actually a subgroup of this. If you compare blue with blue and green with green, or anything in between, red into anything there in general, if I do that, we're comparing cyclic groups. This one's cyclic, the next is cyclic, cross, 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 this one's cyclic. Each Zp to the r power is cyclic. So this thing applies. So we have appropriate subgroup here. And if you do not remember this, then you have to go to step 2, and piece by piece, we have to construct all that. And we can actually prove that piece by piece, those subgroups exist. And then if you remember getting those p to the r power minus s power, which is p to the r power divided by p to the s power, that idea is actually the same as this, m divided by d. The same thing is being repeated here. So piece by piece, we have subgroups, and then take the direct product of those. So the first one here, highlighted in blue, like this. And then the second, third, fourth. And then last one here, green, like this. And we can do that because each component is cyclic. For cyclic, we have the proof. Okay? Here in step 2, assuming that you didn't remember anything about this in cyclic case, I redid all the proof here. But yes, if you did not forget it, then you can use it. If you did forget, then you can either go through with this in step 2 or these, or you can actually go back to lesson 4 and then review there, either way. Here, I'll assume you remember, or at least you are able to go back to lesson 4 or lesson 6 and restudy. So I'll just assume you can do that, and then that's how we moved on. So the conclusion, yes, we do have a subgroup H obtained by these direct products, and then this is P1 to the S1 power times Pn to the Sn power, which is D. So that completes the proof, almost. But if there's a student who are still not completely satisfied with all that, well, let me talk about the isomorphism a little bit. And more precise way is to get all those isomorphism from G to this form. And then instead of starting here, you can take the inverse map of the isomorphism and establish same thing over here and do it here, so that we don't really have to consider making something here and then, as if you're hoping for the best, such a thing applies here magically. There's no magic, as a matter of fact. Whatever here is reproduced here by taking the inverse isomorphism and then work out here. All we have is just applying all those phi inverses, and that's it. That's going a bit too much, so I de-emphasize this part in gray. So that completes section 2, and I'll say that completed lesson 7.